Okay. Physics for dummies. This is a good start to our day, though. So a table weighs 300 newtons, has a cross-sectional area, 4 legs with a cross-sectional area of 10 square centimeters. What's the pressure? So one definition of pressure is a force applied over an area. So the force that we are applying here is 300 newtons. The area, we have 4 legs, and each of those 4 legs has an area of, let's see, let's do a little side work here. So 10 square centimeters is how many square meters? It's not 100, it is 10,000. So if there's 100 centimeters in 1 meter, that means there's 100 centimeters squared in a meter squared. Okay, so 300 divided by 4 is going to be like, what, 70, 75-ish? And then divided by 1,000, or divided by 1,000th is the same as multiplied by 1,000. So this is going to be something like 75,000 pascals. Is that a lot? Is 75,000 pascals a lot? So how many pascals is 1 atmosphere of pressure? (101,000 pascals is 1 atmosphere of pressure. So it's a noticeable amount of pressure, but it's not like a super amount of pressure for sure. Yeah, the recording is going. So yeah, it's a relatively normal amount of pressure, I would say. This is reasonable. On the second problem, we have the pressure at the top of a pipe full of water is 101 pascals. So here's our pipe. So up here, pressure is 101, which is very low, right? So we're getting like close to bubble of vacuum territory for low pressures. And then at the bottom of the pipe, 3.4 meters down, what's the pressure down here? So we have our result from the lecture on the pressure due to a column of water. So the pressure at the bottom of a column of water is equal to the pressure at the top of that column of water plus rho GH. Density of water is about 1,000 kilograms per cubic meter. So definitely the overwhelming source of pressure at the bottom of that pipe is the water above it, not whatever pressure is at the top of the pipe. Right? This 101 is fairly insignificant compared to this, 34,000? Does that make sense?
Dr. Wolfs,
Yes.
so you consider P2 as the total pressure because it's below P1? So like P1 is exerting force and something else. Is that why you chose P2 as the total?
Um, so whether we call them, which one I called P1 or P2 is kind of an aesthetic choice, I guess. Like the subscripts don't matter, but
Yeah, I
yeah,
know.
whatever point is below, right? That's definitely going to be at the higher pressure because yes, it's got the support, the
Okay.
weight of all that water above it. So yeah, 34,101. That's the answer for two. What did you?
But in my book, it says that like 7.5 times 10 to the fourth power pascals is the answer.
7.4 times 10 to the fourth.
Yeah, like I always got kind of confused on like that last part, how they got the answer.
So that's about double the pressure we just got. Oh, actually, so one thing I noticed they were asking for the change in pressure, not the total pressure. So actually, they don't want this 101, just this rho GH. Yeah. So delta P. Pipe full of water. Change in pressure, 3.4 meters. Um, yeah, I don't know where they're getting another factor of 2.
It says here that they like did 300 over like 4.0 times 10 to the negative third power medium squared, and that's how they got 7.5 times 10 to the
Oh,
fourth power
are
pascals.
we talking about the first one or the second one?
The first one.
Yeah, this is so what I wrote down here. This is just like some mental math, but this is 7.5 times 10 to the fourth.
Okay. Okay.
Yeah, this bit in green was for the second problem. You can definitely ask about the syllabus, Miss Jasmine.
So Dr. Wolf, I noticed that for, um, like, so I noticed that chapter 13, like on November 5th, you wrote chapter 13, exam 3. So the same day that we cover chapter 13, we have to do the exam, and it's going to be on chapter 13 as well.
That does seem a little suboptimal, right?
I'm sorry, it seems what?
Suboptimal.
Oh.
So I think I started talking about this in the last class, but I think we should alter that.
Okay, so do you know when our exam is going to be? Are we going to do chapter 13, 14 like on the same day or?
So I think the ideally what we would do is we would have 11, 12, 13, 14 on the next exam, and we would just push the exam back a day.
Would it be 2 weeks then? Or like it depends if are we going to do chapter 14, 15 on like both of them like on the same day, or are we going to do it on separate days?
Yeah, 13 and 14 are going to be the same day. Because 13 is, you've basically had this in chemistry already.
Okay.
So 13 is, we're going to be, just real quickly, 13 is going to, because it's a review from Chemistry 121, I think. And then we'll focus on chapter 14.
And then so then our exam would be pushed back by 2 weeks then, it looks like then. Because instead of being on November 5th, it would be on November 19th. Oh wait, you said 13, 14 together, I'm sorry? You said it's going to be together, right?
So on the 5th, we're going to cover 13 and 14, and then we will take our exam 3 on November 12th. Then we'll do chapters 14 and 15 on November 19th, and then Bob's your uncle.
Okay. Also, so Dr. Wolf, I have like a question. Like, I did the problems in the textbook, and I noticed that sometimes they set like pressures equal to each other. Sometimes they set densities equal to each other. And I don't know why that is. And so, is it okay if I like? I mean, I don't need you to do the problems. I just need to know like why, why we have to set them equal to each other.
Can you pull out a specific example?
Yeah. So. So like for question 26, do you want me to like copy and paste it?
For, you say 26?
Yeah, 26.
Yeah, I can.
Oh, Dr. Wolf's Abigail says that she thinks that question number 2 is wrong with the answer for it.
Yeah, just slightly. Like here, you multiply it by like 10 in the book. They multiply it by like 9.8.
Yep.
Oh, because gravity, you change it to 10, huh?
Yeah, I always round gravity to 10. So yeah, we agree. I just round a little more aggressively than the book you're using.
So I think I know why, because I think, I think it's because it was mentioned. So like in Pascal's principle says that a change in pressure applied to an enclosed fluid is transmitted and undiminished to all portions of the fluid and to the walls of the container. However, that was not said in our, like, we remember we were like going over our toolbox and stuff. That wasn't in there, so is it okay if we just say, I mean, I think it applies to that question, but
yeah.
Can we check?
Yeah, I think that so I think the way I wrote down Pascal's principle was saying that the pressure in a fluid is hydrostatic, which means it's the same
Oh.
in every direction.
Oh, I'm sorry. Okay.
But it means the same thing as what you said.
So so for 26. Okay, so that's what we would write if we set them equal. The pressures. Or
Yeah,
change.
the pressure throughout the fluid is going to be the same.
Okay.
Yeah. So a cork with a 2 centimeter diameter into the bottle, and then he breaks the bottom of his bottle.
Right.
So what's happening here?
Yeah.
What is Yeah, what's happening?
Oh, do you want to go over it?
I mean,
I just need to know why they're equal. That's okay. Yusuf wants you to go over it.
okay. So it sounds like you have a pretty good idea of this. You want to start us off?
Yeah, sure. So so we would set the pressures equal to each other, I guess.
Which
Of
pressures?
the one at the one at the top and the one at the bottom. We say that they're equal.
Like the pressure
The-
here and the pressure here?
The cork in the cork in the bottom.
Okay. So what is the pressure at the top?
So so we have to. So it doesn't say directly what it is, but then it gives us it gives us like the force, and it gives us diameter. So what I'm guessing is that we have to use the force over area one, because with the centimeters or the diameter we have to like convert it to I guess, or like use it to find the area.
Perfect. So on at the top, he's pounding with 120 newtons of force. So the pressure due to that force, right, 120 newtons divided by the area, and it's a 2 centimeter diameter in the neck of the bottle. So we have...
Yeah, so we convert to meters.
Yes. So pi times 0.01 squared, right? Pi r squared. I'm going to do some aggressive rounding here, so it could be upsetting to some people. 0.01 squared is 0.0, like, so 100th squared is a 10,000th, right?
Yeah.
So pi is approximately 3, so 120 over pi is about 40. So dividing by 10,000th by a 10,000th is the same as multiplying by 10,000. So this is 400,000.
Okay. So yeah.
So P2 is also 400,000.
Right.
And that's going to be equal to the force divided by the area. So far, so good?
Yeah.
So if we said pi was approximately 3 on the first one, we can correct that error by saying pi is approximately 3 here. So 1.2 million times 0.14 squared is the force. I guess I'm going to have to pull out a calculator for this one.
Okay. I'll pull one out too.
0.14 squared times 1.2 million is 23,000.
Yep, that's what I got too. Did your son take your calculator again?
He never brought it back,
Oh,
so it's just gone. I mean, it was only a $17 calculator, but still, it's the principle of the thing. So a relatively small tap on a relatively um, narrow area gives us a pretty large force on over a larger area. And of course, this is the same principle that lets the mechanics at an auto body shop lift a car via the hydraulic piston, right? So there's a narrow piston pushing into the fluid with a relatively small amount of force, and it's producing a relatively large amount of force as it's translated through the hydraulic fluid to lift your car up.
oh, Dr. Wolves, I noticed that you didn't write down, like you didn't say that you didn't say why you use P2 as, like you didn't say why you set P2 equal to P1. You didn't say it's because it's hydrostatic. So on the exam, we don't have to do that either.
It would be, I guess, it would be best if we said so. So yeah, you're right. I should have made a note, but no. If this problem were on the test, I wouldn't, require you to state Pascal's principle. I would expect you to use it though, right? So
Okay.
because right, so it's more like a concept, I guess, like Newton's third law, right? Contact forces are equal and opposite, right? That's a concept we need to have in our back pocket, but it's usually not too helpful in calculating actual numbers. Does that make sense?
Yeah, but I don't know, because like we're kind of using I mean, because you said that you don't want us to use what's it called,
Magic
magic
equations?
equation. So kind of like that kind of counts. I would consider it to be a magic equation, kind of, because you're substituting it in.
So, yeah. I mean, the actual formula we used here is really just the definition of pressure.
Okay.
Um, but
So we can just write definition of pressure on the exam. We can just write that.
yeah, force over area is the definition of pressure, or one definition of pressure.
Not that. The why we set P1, P2 equal to each other.
So you're right. So let's be a little more thorough in that case then. So P1 equals P2 because, and then why? Right? Because isn't there a height difference here? Shouldn't we take into account the change in pressure due to the water column above it?
Oh. You mean the one where like the P1 plus PGH equals P2 kind of thing?
Yeah.
I think. Okay. We can use that formula as well. Is that what you're saying?
Yeah, but here
Okay.
H is small. So P1 is approximately equal to P2.
Oh, H is small?
Yeah, the height of the bottle is small. It's only a few centimeters, right? A couple tens of centimeters, maybe.
Well, is it okay if we just say, instead of using that explanation, can we say that P1 equals P2 because it's hydrostatic or something?
Yeah, and it's hydrostatic
Okay.
if there's not a very large... It's approximately hydrostatic if there's not a very large height difference.
Oh, so we have to state that as well?
If you're being a stickler about it. I'm not going to require that level of argumentation.
Okay.
Yusuf, yeah, the bottle is closed, which means we don't have to add another atmosphere of pressure on top of that due to the air pressure.
Dr. Wolves?
Yeah.
So just to clarify, I don't know if you already said it, but we're only doing problems until 11.7?
Yeah.
Okay.
I mean, if
Oh
you
wait, so don't do 11.7. Don't do 11.8 or 11.9.
right, I'm not going to draw test questions from those sections. If you found an interesting question in there, feel free to bring it up, and we'll do it together. But I'm not going to draw test questions from those sections. Okay, do we have any more comments on? Oh, sorry. Go ahead.
No, you're fine. Go ahead.
Do we have any more comments on this problem before we move on to another? No? Okay. $11.48. A compass. Okay, so what fraction of cork will be submerged? And then if you put the needle on it, what fraction of the cork will be submerged? And will it float in alcohol rather than water? Some good questions. This is a good Archimedes principle questions. So, we have some water. We have cork, which is partially submerged. I should use a different color. Right? This part down here is submerged. So if we look at a force diagram of this thing, the weight of the cork is pushing it down, and the buoyant force is pushing it up. And if it floats, like if there's an equilibrium floating position for it, then our sum of forces is going to be 0. Right? Y direction is up. So our buoyant force and our weight are going to cancel. Now, we know that our buoyant force that the water is going to exert is going to be proportional, or it's not proportional, it's going to be equal to the weight of water that the cork has to push out of the way. So we can denote that as where here this density is the water, so the density of the water that gets pushed out of the way is on the left hand side, and on the right hand side we can maybe replace this m with the density of the cork times the volume of the cork. So this v here, maybe we'll do v u for v for the volume that's underwater, and for the amount of cork that's above water, well, actually for the whole cork. So the weight of the cork is going to be its density times its whole volume. That'll be the mass, and then times gravity will be the weight. So far so good? Do people have questions on the interplay between density, mass, and volume here? Variables on the right hand side is the mass of the cork. If we cast it in terms of density, right, mass is going to be equal to the density times the volume, right, by the definition of density. So this mass here gets replaced with this expression, and the buoyancy here gets replaced with this expression. Alright, so G is going to cancel. Oh, sorry, go ahead.
Yeah, sorry. What's the subscript for V? Is that U?
Yeah, maybe it's not the best subscript, but I did U for the volume that's underwater.
Okay, so is that different from the density of water? Or...
Yes. So, in fact, let me just make this VW here. So we'll get W's on the left-hand side, C's on the right-hand side. So
okay.
the density of water times the volume of water that the cork displaces, that gives us the weight of water that or the mass of water that the cork displaces.
So we're just comparing the water and the object in the water, right?
Yeah. So
Okay.
objects will float if they can displace enough water to support their own weight. Right?
Is that
So,
separate from Archimedes' principle?
no, that is Archimedes' principle.
Okay.
So floating means that we have a net zero force with the object, on top of the water. So some of the object is underwater, that displaces water, and if the mass of water it displaces is equal to its own mass, then it floats, and if not,
Okay.
then it sinks. Alright, so we want the fraction of the cork that's underwater. Another way of saying that is we want the volume of water displaced divided by the total volume of the cork. That's right, Jasmine. So if it's going to sink, then the sum of forces won't be zero. In fact, they will be net in the downward direction, and then the object will sink until it encounters a surface that can exert some normal force to support the rest of its weight.
So I'm sorry, because if it sinks and it stops moving, it still wouldn't be zero?
If it stops moving. So when it stops moving on the bottom of whatever the water is in. So if a ship sinks and it gets down to the bottom of Davy Jones' locker, then there's not just a buoyant force, but a normal force from the seafloor that's being exerted upward on the ship.
Okay,
Does that make sense?
thank you. Yeah.
Okay. At this point, we just have to look up what the density of cork is.
It is 0.72 grams per milliliter.
Okay. 0.72 grams per milliliter, is that what you said?
Yeah.
So we got to convert it to kilograms per cubic meter. So instead of 0.72, we're going to have 720. So 720 kilograms per cubic meter. And this is for cork. And on the bottom, the density of water is 1,000. So it looks like the cork is going to be like 72% submerged, right? 720 divided by 1,000 is 0.72. So if you put cork in water, you should have approximately a little more than a fourth of the cork sticking up above the water. Make sense? Are we good?
Where did we get the density values from?
I looked them up online.
Oh, okay. Do we do that for pretty much all of these types of problems?
Yeah. Just go on over to Engineering Toolbox.
Is there a table maybe in the textbook? Let me check.
There is, and it's got a few items on there, but there are many, many items which are not on there.
That's annoying. Alright, thank you.
So part B. What if we put a 20-gram magnet on top of the cork now? Now will it float? So I'm going to make some space. For what color have I not used today? There we go. For part B. Now we have to do a little bit more complicated force analysis, but only a little bit. We're going to have the mass of the weight of the cork, but also the weight of the magnet. Pushing down. We are going to have the buoyant force pushing up. Also, Jazz, where did you get the density of cork from?
Okay, so I didn't really get it. I watched someone do the problem. That's what they put as the density of cork.
Gotcha. Because I think that's actually considerably high.
So I don't know. Right now, I just look. So Yusuf he showed us, or he told me, he asked me, or he asked us if the chart on 11.2, if that's like the density, where we should find the densities of certain solids, I guess, or certain substances.
Yeah.
So it looks like it says that it's 0.24, but that's grams per milliliter though. So so they're different units though. So maybe that's why it's a little bit different. Maybe that's why it's like 0.72.
Well, yeah, it could be 0.72 pounds per square inch, or pounds per cubic inch, or something like that, maybe.
Yeah.
So the 0.24, so 0.24 grams per milliliter, it's going to be the same as 240 kilograms per cubic meter. So actually, it's with that value of density, it's only going to be 24% submerged.
Let's see what happened then. That's weird. So what question is that again?
48.
48. Okay.
Right.
Yeah, I guess he did it wrong then.
But it's the method is probably perfectly fine. He just looked up a value
The
for
wrong
cork
one.
that was
Sorry about that.
No, it happens. It absolutely happens. So part B.
It was him. I still use him, I guess.
All right. So for part B, we're adding some extra mass on top. So we would like the sum of forces to be 0, because that's what it takes to float. In other words, we would have buoyant force minus weight of the cork minus weight of the magnet equals 0. So buoyant force equals the two weights. And we can play the same game, right? So rho water v water times g equals density of cork, volume of cork times g, plus mass of the magnet. G's can cancel out of everything. Now we can't do exactly like we did on the last problem, where we just solved for VW over VC. We can't do that because we have another constant term hanging around. But what we are told is that the mass of the cork is 10 grams. So we can just solve directly for how much volume that must be. So the volume, right? So density is mass over volume. So volume we can think of as mass over density. Okay, so this is a pretty small number. We have what, 4, again, I used a calculator, makes me feel a little dirty, I don't feel quite right. 4.2 times 10 to the minus 5. Alright, so with
Dr. Also, wait, how did you get your numbers, like 0.01 and 240?
so 10 grams is 0.01 kilograms, and then the 240 is just the density from part A.
Would we add 0.01 and 20 together? Like 10 and 20? Because that's also, like, exerting, like,
It is.
I don't know, like, force. So should we add 0.01 and?
We're keeping
together?
track. We're keeping track of the mass of the magnet in the second term on the right hand side over here. Right. So the mass of the magnet is definitely exerting weight on the cork, but it doesn't have the same density as the cork.
Okay, got it.
Yeah. So we're not able to lump it in.
Okay, got it.
So now we can solve for VW directly. Or I guess if you were operating with, if you were sufficiently caffeinated, a state which I do not find myself in, you might have realized, hey, density of quark times volume of quark, that's just mass of quark. And we know what that is. So something like that. So this is like 3 times 10 to the minus 5. So the volume of quark that we need below the surface is in fact smaller than the volume of quark which we have, so it'll float. And we can calculate the percentage. So now it's going to be like 71% submerged. Questions or comments? Yeah, rounding and sig figs do play a role. 100%. But it's all in the same neighborhood. For the last bit, we're asked if this magnet and quark will float in ethyl alcohol rather than water. And so we only need to alter one thing, right? So we take this expression from the last step in pink over here. The volume you would need for alcohol is going to be equal to, right, the mass up top divided by the density of alcohol, which, yeah, is not 1,000 kilograms per cubic meter, but only about 790. And so instead of with water, we only needed to displace 3 times 10 to the minus 5 cubic meters. With ethyl alcohol, we would need to displace 3.8 times 10 to the minus 5 cubic meters. So more of the quark would be submerged, but this volume that we would need to be submerged is still smaller than the volume available. So yeah, the quark and magnet would still float in alcohol. So if you are on a hiking trip and you need to make a magnet and you don't have water but you do have vodka, you're in luck.
Dr. Wolves, could we also have said compare the densities and said that if the density of the that's what Yusuf said. So if you could what we could have done was that we could have compared the density and then compared it with alcohol, I guess, and said that if it's less than if the density of magnet in the quark is less than the density of alcohol, then it will float. Can we do something like that?
Yeah, you could absolutely have done something like that. So, for example, you could have said the net density of the quark plus magnet is equal to the mass of the quark plus the mass of the magnet divided by the volume of the cork.
And then we said like, oh, it's less than the density of alcohol.
Yeah. So yeah, if you go this route, you get 714, and that is definitely smaller than the density of alcohol. So yeah, it'll float in alcohol.
Okay, thank you.
The toolbox for this chapter. Yeah, we can definitely talk about that. It is a small toolbox. We're not adding much. This is like the definition of pressure. Like maybe deserves to be called a tool, but maybe not. But the definition of pressure is a force over an area or an energy per a volume. Right? The units work out the same on those. And then we also need to remember the definition of density. We also have Pascal's principle. Right, then pressure at the same height constant depth, maybe you would say. Alright, I see a bunch of questions scrolling in the chat. I will get to those momentarily. And lastly, the buoyant force. If we end up skipping anything from the syllabus, it'll be thermodynamics. But I do want to get to thermodynamics in our last lecture, for sure. This coming Friday, we will do 12 and 12 by itself. And then when we come back on the 5th, we will do 13 and 14, and on the 12th we'll have the exam. I mean, thermodynamics is connected to everything, right? So thermodynamics is the study of why large systems tend toward the averages they do. So we're gonna not scratch it. We're gonna barely scratch the surface of it in this class, but there is a whole lot of study that you can do in thermodynamics. Isn't thermodynamics really important for the MCAT? I don't know if I would say really important. Like, you do get questions on the MCAT, like what's the work done by an isothermal expansion. So I mean, thermodynamics questions do exist on the MCAT. Someone asked about if we're going to go over test solutions. Yeah, that's the first thing we're going to do on Friday. So I've only graded a few tests so far, so I'm not very far into my grading. But everyone I have graded so far did better on exam 2 than exam 1. The toolbox for chapter 12. Okay. Yeah, this week is still fluids. So we are adding, I think, 3 things in chapter 12. Yeah, I definitely do recommend doing some chapter 12 problems before we get to the lecture. That's absolutely true. And I don't mind doing a preview of chapter 12 either. So the first thing that we are going to learn in 12.1 has various names. It's sometimes called a constitutive relationship. It's sometimes called the continuity equation, sometimes conservation of flow. But basically the idea is if you have a pipe and you are pushing fluid through it, the amount of fluid passing any point in the pipe per second has to be constant everywhere in the pipe, because everything that you are pushing in from one end has to come out the other end. So we have a pipe, and maybe it's got shapes and bends and whatever. But the amount of stuff, the amount of fluid that you are feeding in one side, right? So R kilograms per second, right? That much stuff has to come out the other side. And in fact, you have to, at any arbitrary line you might draw on the pipe, the flow rate has to be the same. So that's what this relationship is saying. The cross-sectional area of the pipe times the velocity of the fluid gives you the flow rate. And so the product of cross-sectional area times velocity has to be constant everywhere in the pipe. So if your pipe gets thinner, your flow rate has to get faster. That is in fact why if you put your thumb over part of a garden hose, the water sprays out faster. You have narrowed the pipe, so the velocity of the water must increase.
I'm sorry, you said the rate should be like the same?
Yeah, the flow rate has to be
So
the same everywhere in the pipe.
So the flow rate is the cross-sectional times the velocity. It's not just velocity.
Right, because if you have a larger diameter pipe, the water may be moving slower, but there's more of it.
Okay.
right? So the amount of water in mass per second is the same. The second thing we're going to add is called Bernoulli's equation. And this is a conservation of energy for fluids. So this is, note that all of these terms here have units of energy per volume, right? So this is like gravitational potential energy per volume. This one is like kinetic energy per volume. And then the pressure, right? Remember, I kept saying before, the pressure can either be a force per area or an energy per volume. Okay. So that's Bernoulli's equation. And then the last thing that we are going to, well, we're going to look at a couple things, but we're going to look at Pucell's law. So Pucell's law talks about the flow rate. The flow rate through a region is equal to the difference in pressures divided by the resistance to flow. And this resistance to flow is slightly complicated. So it encompasses the length of the pipe, the width of the pipe, the viscosity of the fluid. Yeah. That is the Greek letter eta. Eta is the traditional variable name for viscosity. Yeah, you don't really. Viscosity doesn't really get talked about in detail in chemistry. Yeah, this is our three things from chapter 12.
So, Dr. Wolf, are we going to be skipping some sections of 12 then?
Yeah, so 12, 5, 6, and 7 are interesting, but 5 and 6 I think are really, they are, I mean, they should be read, but there's nothing that we can realistically test on in those chapters, because you just need more mathematical background to properly treat them. And then,
so what about 12 points? Oh, sorry. Go ahead.
Oh, I was just going to say, in 12.7, there is some, the 12.7 is about diffusion. And if you know about colligative properties from chemistry, this will give you This will give you an explanation for why membrane pressure is the way it is. Um, but yeah, I think this is better handled in chemistry. And the idea of diffusion is there's too much in the diffusion chapter that is really more mathematical background. So I'm not going to test on that as well.
So we're just skipping 12.5, 12.6, and 12.7.
I mean, you should definitely read them because it's good to have that knowledge in the back of your mind for when you move on in the world, but there won't be test questions.
Okay.
Yeah, that's one reason I chose this book. I figured that a pretty good book, which was free, was way better than an excellent book, which was $200. Also, here is something that I found amusing that I'm sharing with you. Do we have any other questions? What I really like about this comic is how angry the physicist looks. Problem 27 from chapter 11.
Yeah, I don't need to go over it. I just want to know why the volume is the same in the pressure, because this one it's like a little bit different than like the one that you went over, like 26.
Mm-hmm.
So it's just parts A and C that I'm confused on. I mean, I don't need all of it to be done. I just need to know why for A the pressures are the same, the initial pressure, the input pressure and the output pressure, and for C I need to know why the input volume and output volume is the same.
That is a good question. Actually, let me draw this out because I think a picture is worth a million words here.
Oh, so, did you see question 27?
Yes.
Okay.
So when you have a hydraulic setup, the thing that they're not saying explicitly is that these two things are connected. So there's an input on the left, there's some hydraulic fluid, and then on the right there is a much larger output piston. Okay. So if you want the right, so it's just like the wine bottle problem, where the pressure over here and the pressure over here are the same. So that's part A. Does that make sense?
Yeah. So on the exam, we just write Pascal's principle. We don't have to explain it.
Well, I mean, if it asks you to calculate a number, so we're gonna do that.
Yeah.
So P1
Okay.
is going to be the force exerted over the area, and that's going to be equal to the ratio of force to area on the right, which is P2.
So would we say that it's because it's hydrostatic or something, or could we just write Pascal's principle?
Yeah, Pascal's principle says that everywhere, as long as the fluid is the same height, the pressure is the same. Right? And even though, yes, we are moving pistons up and down a little bit, the change in height is going to be small.
Wait, how is it going to be small?
Compared to the pressure, right? So we deal with it more thoroughly in chapter 12, right, where we have pressure plus rho GH plus, right? What we should really be saying is that that we should really be saying Bernoulli's principle, right? That the energy at the left and the right is the same. However, the fluid is not flowing, so there's no kinetic energy. And if the change in height is relatively small, right, compared to the pressure that we're exerting, then P1 is going to be approximately equal to P2, and that's Pascal's principle, right?
Oh, okay. But how do you? I don't. Can you show me why? Like, because I can't see how there's not a change in height. Like, could you draw it for me, please?
Yeah, there is a change in height for sure, but if the change in height is, say, 1 meter, right, then the size of rho GH, and here we're going to be using some hydraulic oil. It probably has the density is going to be less than water, but not like a lot less than water. So if we raise this car up by a meter, then this number has something like 1,000 times 10 times 1, so it's 10,000 pascals, right? But the pressure over here, if we're exerting, say, 500, or if we're exerting, say, 500 kilograms worth of force, so our pressure is going to be 500 kilograms times G divided by a cross-sectional area. And if this is only like a few centimeters across on the small end, then we have something like, again, these are numbers that I kind of made up, but they're reasonable sounding numbers, right?
Yeah.
So 5,000 divided by pi r squared. We get something like 600,000. So there is definitely a change in height, but the energy associated with the change in height is small compared to the energy associated with the pressure, right? Because 600,000 is a lot bigger than 10,000. Right? So when we add them together, 600,000 plus 10,000 is approximately 600,000. Does that make sense?
Okay. Yeah, because I think you went over this in lecture actually too.
Yeah. So saying that the pressures are exactly the same, right? It's not going to be exactly correct because the heights are going to be a little different, but the height doesn't matter that much.
Okay.
with the pressures involved.
Okay.
Uh,
And
it's like
yeah.
it's one of my. This is a saying that I like a lot. What's the difference between $1 million and $1 billion?
There's a big difference.
Yeah, the difference between $1 million and $1 billion is about $1 billion.
Yeah. So it's I get it.
So that's
Yeah.
exactly what we're saying here. What's the difference between the pressure energy and the potential energy? About the pressure energy.
Got it. And for C, for volume, I want to know why they're like the input volume, the output volume is the same. Is it because, let's see. I guess it's because they have the same, I don't know, like, or you didn't, I don't know why, actually.
So if you push a certain volume of hydraulic oil out of the way, you have to make room for it over here. Because we've got a closed system. That oil has to go somewhere.
So what principle is that? Like, is it like what? So I know, like logically, yeah, that makes sense. But what principle are we basing that off of?
Let's see. I don't know if there's necessarily a principle. It's really a geometric consideration, right? Because if this is a closed system, then the total volume of oil in this system has to be constant.
Okay, so on the exam, we can just put V1 equals V0 without explaining it.
Well, I mean, draw me a picture.
Okay, but
Picture's worth 1,000 words, right?
Oh yeah. Okay, so if I just draw you, then I'll be good. I don't need to write anything right next to it.
Hey, maybe saying something like the total volume of the closed system is constant, something like that. But yeah, you don't need to say a lot. Yeah, I think Elon Musk is only temporarily going to be a trillionaire, though. And he's only a trillionaire on paper until Tesla stock takes another dive. Right? And you know that man cannot keep his mouth shut. So he's going to tweet something stupid this week, and Tesla stock's going to fall, and he won't be a trillionaire anymore.
Wait, what? Did you guys say that he became a trillionaire?
Yes, he is currently a trillionaire.
No, wait, no. When did that happen?
Like last night.
Really?
I think so.
Let's see. No, it still says 200. Like Forbes has it listed as 200. Like his net worth listed as 220.1 billion.
They're calculating based on the amount of money that SpaceX was able to raise in a share offering earlier this week. So they sold a small number of shares for $100 billion. And then we're like, well, if they sold the whole company at that share price, the company would be $3 trillion. And Elon Musk owns half of it.
Oh, so you're talking about his app? Okay, I get it.
Yeah, so it's still a little speculative, but and part of that's because SpaceX just beat the crap out of Blue Origin for the NASA contracts, and Bezos is so hurt over it that he's actually suing NASA, which definitely is not going to go well for him. If any of you enjoy space and space news,
Welcome back, everyone, to another space.
I follow this guy on YouTube, and every Monday he makes a video where he compiles news together of all the space launches and space news that happened in the last week. And yeah, so 15 minutes at the start of your week and you're caught up on everything that happened in space. Only for nerds, though. It's kind of amazing how many space launches there are. Like, on an average week, there's 3 or 4 rockets being launched with new satellites. I think that means you're a nerd, Abigail. It's alright. You can embrace it. Do you have any other questions? Any other problems that people want to go over? All right. Well, let's end here for the day then. And question 31. Okay. Hey, sweetheart, I'm still in office hours.
Yep.
I love you, darling. Okay, how do manometers work? And also, that is a word that is fun to say.
I absolutely do not know. That's why I asked. And it seems like for this one, the pressures are the same again. I don't know why the pressures are the same, because I don't know how a manometer works.
Okay, so a manometer is a curved bit of tubing. I'm going to do my best to... and it's connected to 2 different fluids, one on each end. So let's say on one side is water, and on the other side is mercury. Okay. If we do this with gases, it's a little bit different than doing it with liquids. Okay. But the idea here is that we've got actually 2 columns of fluid, right? We've got this water pressurized because there's a rho GH component here. And we've got the mercury pressurized because of a rho GH component here. and we'll say this is rho of the mercury, height of the mercury, height of the water. Okay. If they meet in the middle, then they have the same pressure. If the mercury is at a higher pressure, it will push the water out of the way, and we'll have mercury coming up this side. If the water pressure is greater, then it will push the mercury out of the way, and we'll have water coming up this side. So what we want to say, we want to pick our heights such that our rho water G height of the water is equal to the height of the mercury column on the other side. And this is actually where the origin of measuring pressures in millimeters of mercury comes from. Because the pressure on this side, right, what we're actually measuring is we're measuring the height of that column of mercury. Right? So when we're measuring a pressure, we're measuring how high does a column of mercury have to be to give us that amount of pressure. G's cancel, and we get so the density of mercury is, I actually don't know that one off the top of my head, 13,600. The height is only 300 millimeters, so 0.3 meters. And the density of, if I could draw straight lines, that'd be amazing. Density of water is 1,000. Calculator time, and this is about 4 meters. So if you're not able to have a column of water at least 4 meters tall, then you are not able to generate the kind of pressure that 300 millimeters of mercury would produce. Questions or comments? Question 17. Okay, so no comments on this problem?
So we don't have to write anything for this one? Like, we can just say, like, the pressures are just the same?
So when the fluids meet in the middle and the pressures are the same, that is the maximum water pressure that the manometer can produce. So right, if we had a higher water column than that, we could produce higher pressures, and we wouldn't need all 4 meters of it, so we would get something like this. Then maybe the mercury would fill up to here, and the height left over would be would be enough to balance out the column of mercury on the right hand side.
So on the exam, we would just put that we set them equal to each other because we want them to meet halfway.
Yeah, so that's right. So
Okay, if that's what we put, okay,
I think
I'll just
there-
put down the exam.
I think there's some expectation that probably you've had manometers in chemistry already, like you have a little bit of idea of how they work. And so the question is asking about the minimum height of a manometer.
So they always have to be they always have to meet halfway. Is that how it works with manometers?
They don't always have to meet halfway. In fact, the way we use them for measurements. So if we know what the pressure of the water on the left-hand side is, right? So say we're measuring something. It doesn't have to be mercury, right? It can be anything. So we know that the pressure right here is equal to rho GH. And in fact, the original manometers had mercury in the middle and then would connect to fluids on either side. So we might even write something like this. Right? So some other fluid here. And then there's mercury in the middle. So if we can calculate, or we know somehow the pressure on the left-hand side, the pressure on the right-hand side is different, right, by an amount proportional to this height in mercury. So so this right here, that's why we end up measuring things in millimeters of mercury.
Okay.
Right? Because the difference in pressure between the two sides is enough to cause the mercury to rise higher on one side.
All right.
Does that make sense?
Yeah. Thank you.
I would say that these problems all tend to be shorter than the problems from the last several chapters. They're much more plug and chugs. So my feeling is that I will probably put more questions on the test, but they will be smaller questions, and then it'll be fewer points per question. Alright, so last problem of the day, we got water towers. So water towers, this is the main way we, not in Las Vegas. In Las Vegas, we mainly use pumps, but in, say, New York, it's really common to see tall buildings with a water tower on their roof, and this is to make sure that there is sufficient water pressure all the way through their building, so that everybody in the building can take a shower. So if we have a water tower, like so, and pretend this is an actual square. If we want a gauge pressure down here of 300,000 pascals. That pressure is due entirely to the rho GH, like the pressure due to depth. Does that make sense? Yeah, so our height is just going to be, right, gauge pressure divided by density divided by gravity. So 300,000 divided by 1,000, 10. So that's what, 1, 2, 3, 4 zeros that get canceled off? 30 meters. So, we've been saying that the pressure in a closed fluid system is the same everywhere at the same height. And that is true no matter how horizontally separated the user is from the water tower. Right? So if this pipe, if this is 10 miles, that it doesn't matter how long that pipe is. Like if you're 10 miles from a water tower, but you're still 30 meters vertically below it, you get water pressure, and you can take a shower. Yeah, on Friday we'll be working some chapter 12 problems. So we'll be starting by doing exam solutions, and then there will be a chapter 12 lecture, which won't be that long because I don't think that I think this is like the material doesn't take that long to get through, and then we're going to do problems. Yep, that is fair, Jasmine. I will attempt to remedy that for chapter 12. We've got a submarine on the bottom of the ocean. Submarines are on the list of things that I cannot draw. So I'm going to draw a box. We have a hatch down here, and it's circular, right? But we don't need to draw it circular. We have a force from us pushing. We have a force due to the air pressure inside. We have a force, and then we have a force pushing down, which is due to the water pressure. Okay, and we'll say that up is the positive direction. Now, this sub is 25 meters below the surface of the ocean, so water's not purple. There we go. So buoyancy is something that's going to be affecting the sub as a whole. But it's not going to be affecting the door specifically. Alright, so the force of the water, let's say, is equal to the pressure due to the water times the area of the door. The area we can calculate, it's circular, it's 0.45 meters in diameter, so we can calculate that. In fact, maybe we do that real quick. Alright, so this area, the area of the door is like 0.15 square meters. 0.16. Alright. The water pressure at this depth is going to be, right, the pressure at the top, which is 1 atmosphere, the force of the air pressure inside the sub, we're told it's 1 atmosphere. So it's going to be and the force of the push, that's actually just what we're trying to calculate. So the minimum amount of force needed to open this door that would cause, so we need enough force to cause this door to accelerate, so which means we need a situation in which FP is just a little bit bigger than the force it would take for the sum of forces to be 0, right? So we can solve for how much force it would take to equalize the force, and then we just think, well, any smidge of force more than that would actually cause the door to open. Okay, so you may have noticed that I left atmospheres in the red scratch work up here. And I did that on purpose because, so FA, the force of the air due to the air inside the sub, is going to be 1 atmosphere times area. But there's also a 1 atmosphere times area term in the force of the water pushing down on the sub. So those two bits are going to cancel. So we're looking at 40,000 newtons of force. That is not an amount of force that a human body can provide. So this poor sailor is not going to open the hatch. Questions, comments?
But why did you add PGH to 1 atmosphere?
So there's 1 atmosphere of air pressure up top, which is pushing on the water, right?
Okay. Got it. Sorry, yeah.
Okay. Why do we divide the diameter by 4? Because we actually need the radius to calculate the area, right? So whether it's pi radius squared or pi diameter squared over 4, that gives us the same thing. That's right. So diameter over 2 quantity squared. All right. Anything else we want to hit really quickly before we are done for the day?